Just a quick reminder, of course, this is our last week online, and we have the enviable time slot of Friday afternoon at 2:30. Sorry, my calendar's over here. And that'll be our last online class. And then we have reading week, and then we'll be back in person. So we'll be in Ellis Auditorium for the Section 102 students. Alrighty, let us dive in. So speaking of Fridays, last Friday, we had a class where I tried to talk about or show one quick example of a matrix form for working with equations. And there was this duality here in terms of how we could choose to represent systems of linear equations. So this is sort of the traditional. And this is the augmented matrix that represents exactly the same system, because all we have to do is keep the coefficients and the right-hand side values. And the reason we can get away with just dealing with the coefficients is that the column indicates the associated variable. We are not Wild Westing this. If I have X's, Y's, and Z's, I'm just going to consistently put X as the first variable, Y as the second variable, and Z as the third variable. Well, if I do that every single time and do that consistently, when we do things like, hey, I'm going to take 3X and subtract 6X, the X's don't actually change, but these are the only things that are going to interact. All we do is the net effect of that kind of subtraction is to modify the coefficients. Well, then why don't we just show the coefficients and let the place markers indicate the variable that's associated with it, with the one special thing being on the right-hand side here, just being by itself. So it's distinguished from the others by that vertical bar. That's what makes this an augmented matrix, is this sort of separation between the data types, if you like, between coefficients of variables on the left and the just straight values on the right-hand side. Sorry, just a quick question there. Do you know if all your classes will go back to being in person? That is what we're hearing. There is, oh, sorry. If it was planned to be back in person, all the classes will be back in person. I think some of them are blended formats. So like 172 has a blended format to start with. So you'll get details about that. But any class where you have a lecture that was supposed to be in a room, that will be in a room when we come back in at the end of February, early March. All right. Now, when we're looking at systems of equations and we look at the matrix form, it's actually quite nice because we kind of throw away all the murkiness or the confusion that the variables kind of block, and we see some really lovely structures. These are all three equations because every equation corresponds to a row. Just going back the slide here. There are two equations here. We got two rows, and these all have three variables, and that's three columns before or to the left of the vertical line. We have three rows and three columns before the vertical line, and each one of these is associated with a variable. 3 rows, 3 columns, 3 rows, 3 columns before the line. Now, you'll notice going left to right here that there's a significant difference in terms of numbers of zeros. And it's important to recognize that we really, really, really like zeros in these matrices. Why? Because if we translate this back to traditional formats, back to a traditional format, and if we remind ourselves that this first column would go with a variable like X, second with Y, third with Z. In another scenario, it might be X1, X2, X3, or alpha 1, alpha 2, whatever. Whatever the three variables in your problem are. When you have this format here, look what you get for X. X is 1X, and there's 0 Ys and 0 Zs equals 3. Oh, and the second one is 0X's plus 1Y, 0 Zs equals 1. and z equals -2. Solution can just be read directly from matrix. From the matrix. So this is pretty awesome as solution sets go, as forms of matrices go, because if I see this element or this row by itself, I can read off with some experience that, oh, that translates to x equals 3. I know what my solution to my equation is, at least for the x variable. Next row gives me y, and the final row gives me z. And we might have to do some work to get to there. In fact, we're going to see there's sort of an intermediate form, which is this one here. And this one's almost as nice, except, well, it has lots of zeros. In fact, it has zeros in this nice location here, which is all in the lower left-hand side of the matrix. And you see these diagonal ones. What does that make this into? It makes it almost as easy to solve as the last one, just with a little bit more work on your end. If we take the third equation, it has exactly the same form we had here, right? This equation and this equation are the same. So we can read off that that means z equals -2. And then we can go back up to the next equation, equation 2. Once we know what the value of z is, then we have an equation that only involves y and z. Oh, so let's take a look at that equation. That's y plus 3z equals -5. That's equation 2. Actually, let me erase this for a second. We'll do it all in red. That's y plus 3z equals -2. But we said that z has, sorry, -5. -5. But we said that z was -2, so we can put that in for z's. So we're going to get y plus 3 times the -2 value for z's equals -5, or y equals -5 plus 6, y is equal to 1. And so we get that, we get that. And then you can see the structure here, I hope, that, oh, because this, we now know what z is from the last row. We now know what y is from the second last row. We can now solve for x in a relatively straightforward way because we know what y and z are, and we know what the right-hand side is. Let's do this in green. Equation 1 tells us that x plus 2y minus z equals 7. And that's x plus 2, and we had y was 1. And we had minus z, which is -2, equals 7. And if we shuffle all that around, we actually have plus 2 and plus 2 again. Bring it to the other side, it's -4. And we're going to get z equals 3. You're like, oh, that's actually the same system. Sorry, not z, x. X equals 3. That's fair. So we solve for x by bringing this +4 over the other side to get -4, and we get our x's there. And what you see is that's the same solution as this system here, but it's a little more work to actually get all 3 values as our solution. It's much easier to read off in this form here. This form is just a mess. Need to do a lot of work, to do a lot of canceling, adding, all that kind of stuff before we identify the solution. Okay, so there's the generic form here on the right-hand side, this sort of just a bunch of numbers in a matrix. Then we have this form here, and it has zeros in the lower diagonal, ones down the diagonal as much as possible. We'll talk about the fine details of that. And then we have the one here where, focusing on the left-hand side, specifically same for these ones too, it's ones down the diagonal and then zeros everywhere else. And diagonals, again, I'll put a little asterisk on that. Those have names because they represent different ease or difficulties of producing a solution directly from the matrix. So this form here is called RREF, or row reduced echelon form. And we'll talk about the details of that on the next page. This one here is often called just row echelon form. Sometimes it's called upper triangular, though there's some fine distinctions about that you don't care about right now. Upper triangular. And you can kind of see why that would be called it, because on the upper part of the matrix, there's a triangle you can kind of carve out. And then this has just general, no specific name. All right. And this is the easiest to analyze for the solution. This is hard to analyze for the solution. To get a solution, what are X and Y and Z? And this one here is straightforward. To get solution. The process that we used there, where we got Z equals, put in the matrix, sorry, put it in the row before that, and then we got the next value, and then we got the third value finally. That is a technique called using back substitution. And you can kind of see where it got that name from. I'm going to substitute Z into the equation before, one equation back, and then I'm going to substitute Y and Z back into one equation back in the list, and so on. And so that lets us solve it not as easily as the first one, but certainly way easier than the last case there. Yeah, so the placement of the ones and zeros is exactly what we're going to talk about. We are going to focus on this one here, and I'm actually going to define that for you on the next page. The definition for this is in the online textbook. We are going to focus largely on our RREF. That's going to be our go-to because of lots of nice properties for it, quite frankly. So yeah, basically, if you know RREF, you're good. It's sometimes helpful to recognize you might get this form along the way, but RREF is going to be our thing. So what is RREF? Sorry, is there a quick chat there? Is there a lower triangular form? Not in what we're doing, not for solving things. Traditionally, we just stick things in the upper right matrix. However, anyone who does numerical methods a little later on and large-scale data analysis, you talk regularly about upper triangular matrices, lower triangular matrices. It's a different context than what we're doing now, though. So yes, they do exist. Yes, they're relevant. There's all sorts of fun, there's all sorts of even more fun linear algebra than we get to see in 174 involved with that. But beyond the scope of this course, there's lots of names for different kinds of matrices, but upper triangular and lower triangular are definitely common terms. For us, RREF is going to be the one that we're going to be focusing on. All right, so a bunch of terminology to throw at you here. Gaussian elimination. So you'll often see this online as just, the short form GE. It's Gaussian elimination. This is invented by Gauss as a process that you can prove systematically always gets you to the row reduced echelon form. So whatever matrix you start with, it'll have a row reduced echelon form to it, and it'll be unique. There's only going to be one form available to you. How do you get it? Well, we talked about these row operations before, and the idea is these are all analogs to reordering, adding, multiplying traditional equations. Right. Just going back a couple of slides for a second here. When you have a traditional equation like this, you're allowed to take this entire equation, multiply both sides by a number, say by 2, and then you're allowed to subtract this whole equation. Why? Because you're maintaining the equality here, and you're adding 2 equal quantities to each other, or you're adding the same amount, sorry, you're adding the same amount to both sides when you add the equations or subtract the equations. And all we're doing here with the row operations is doing those transformations, making those manipulations, but with just the coefficients, which turns out is all we need to manipulate with those. So you can switch, you can swap, you can reorder the rows, that's what permuting means. You can multiply or divide any row by a non-zero number, so you can just scale it. So yeah, we'll see this all in context with some examples. And then you can add or subtract a multiple of some row to get a new row. So again, you'll see this in action, but basically you can shuffle the order, you can just scale a single row, or you can scale one row and another row and add and subtract or subtract them to get a new row. What we're going to be looking for is this RREF. And what is magic about it? It's this specific sequence of requirements. So in each row, there should be a leading one. And by leading one, I mean, it's right here, from left to right, the first non-zero value should be a 1. So you're going to have 0, 0, 0, 1 stuff, that's okay. 0, 0, 1, some stuff, that's okay. 2, 0, 1, that would be bad. 1, 0, 0, 1, that's actually okay, because the first element in it is a 1. So basically, you can't start a row with a if you're going to, the first row, the first value as you move from left to right has to be a 1. So what would also be wrong? 0, 0, 0, 2, and then some stuff, that would be wrong as well. Okay. That's just this condition here. There's more to it though. So I'm going to erase these for a second because they're not good to have on the page permanently. If a column has a leading 1, then all the other elements in that column, so say we have 0, 0, 1 and then some stuff here, everywhere else in that column where that 1 is has to be zeros. I'm only allowed one of these non-zero values in a column. And I'm just going to go back to that example we saw a little earlier here. Notice that's what we have structured here. We've got, if I have a 1 as a first element, that's fine. And all the other things in that column are zeros. Next row, I go across the 0, 0, 0, and then my first non-zero is a 1, that's good. And in that column, I only have zeros for the other values. This row, 0, 0 is fine. My first non-zero is 1, that's perfect. And then I get a double check that, yes, the rest of that column is all zeros. And the last thing is that when you have these 1s, in principle, it could have been a 1 at the top, then 1 further in, then 1 further back. We're not going to allow that. It's going to be a staircase from the top left to the bottom right. So the 1s are only going to go in this kind of stair-step diagram. The 1s on a lower row have to be further right than any earlier ones. And again, this all becomes intuitive once you do about 5 examples. You'll see like this is what makes it easy to generate an instant solution to the system of equations. And yeah, let's just see how this works out. So here we have a system of equations, and we're just going to solve it. So the notation that we're going to use, it's helpful to track for yourself what you're doing to the different rows. So we're going to call this row 1 and call this row 2. And so you'll see this in the online textbook as well, that we have this R1 minus R2. Some online guides, and I think maybe the textbook as well, sometimes ask you to only do one operation per step. I think I mentioned this on Friday. I think we can be a little more freewheeling with this. We're just going to let that go to voicemail. It's going to be annoying though. Pardon me for 1 sec. Sorry about that. All right, row 1, row 2. And yeah, we're going to do multiple operations at once. So what we're going to do, remember now our goal is explicit. We're going to try to get leading 1s rather than leading any other values. And we're also going to try to get zeros around those 1s. So if I'm just looking at this equation here, I think maybe I could divide this by 2 or something. That might be one operation that'll give me a leading 1. And yeah, why don't we do that? So let's take row 1. and we're going to divide it by 2. Now, it's not my first choice because we have this value here that the 1 goes in here, and dividing by 2 gives rid of a fraction, but we can live with it. So we divide that row by 2. We're going to get 1, 3, a half, and then 4. So a lot of mental math here, just doing basic multiplication and addition operations, though. Now, the next thing would be trying to get a 0 around that. I'd really like a 0 here. The easiest way to get that, I think, is to take 3 of this row minus 2 of that row. That's going to give me 6 minus 6. That's going to give me a 0. So we can have 3 times row 2 minus 2 times row 3. So again, all the kind of stuff that you would have done when you learned how to solve systems with linear equations, just here working only with the coefficients. So the whole point of that exercise was to get a 0 here. That's perfect. Then we have 3 of these, 18, minus 2 of these, that's 18. Oh, that's 18 minus 18, that's 0. Perfect. Then we get 3 minus 4. 3 minus 4 is minus 1. This last one, to be a bit careful. 8 times 3 is 24. 24 minus 28 is minus 4. Perfect. All right, then we could get rid of this -1 thing here. Let's keep row 1 the same from the previous version. So these references here to row 1 are always just back to the previous example. And then row 2, I'm going to just do -1 times row 2.
I have a question.
Yep, go ahead.
What are you referring to as row 3? Is that
sorry.
R1 divided by 2?
That's that's R1 and R2. Sorry, I'm getting ahead of myself there. Row 1 and row 2. You're right. That's all there is. Thank you. 3 R1s minus 2 R2s. My apologies. All right. Let me just pause then and interrupt with a quick clicker question. So take a look at that matrix and ask yourself, is that in our RREF form? Responses. All right. Not too bad. Okay. Again, this is a new form, so that's totally fair. The answer is to RREF is not yet. We do have the ones in sort of a staircase down. So this row has a 1 as a leading 1, and then other stuff, and that's fine. This row is 0s until it's a 1, so that's fine. However, there's that other requirement, which is if a column has a leading 1, then all the other values in the column and the other rows have to be zeros, And that's a problem here. So this part here is what's not RREF. The first column's fine. It's got a 1 and zeros in the rest of that column. That's fine, but this one here is wrong. So, and again, if you think of solving, we don't really want to have that value there. So what we're going to do is one last step where we take, what do we need to do? We need to have R1, and I just want to subtract this. I'll subtract a half of this. That should fix it nicely. So I take R1 minus a half of R2. And again, there's different ways to play with the rows and stuff, row operations that we're doing here. The important thing to recognize is once you get to the row reduced echelon form, it will be, with one tiny little asterisk, unique. So if you get an RREF through one process and I get one through another process, they are going to be the same final answers, even if we took different routes to get there. So you might look different along the way, but your final answer should look the same. So here, we're going to have 1 minus 0, 3. Sorry, 1 minus 0 is 1, 3 minus 0 is 3. And then a half minus a half is 0. That's the whole point of that. And then 4 minus a half of 4 is 2, 0, 0, 1. And we keep that same, R2. All right. This is is in RREF. And we can read off our solutions here with a slight change of notation. Then we are told in this particular instance that the variables we're talking about, the variables that represent, these coefficients represent coefficients of these specific variables, not x, y, z, but x1, x2, and x3. So put that in here. Because this number is in the third column, it means it's the coefficient of x3. And so we can read off our answer here. I'll just translate both equations side by side. We have x1 plus 3x2 equals 2, and we have x3 equals 4. And so what we get is a solution. One of them is unique, and this one here is interdependent. It could be either one. And so once we pick one of the values, we would get the other value, but we have some choice. So we'd have an infinite number of solutions here. And let's say it with x1 would be equal to 2 minus 3x2s, but x3 has to equal 4. So anything that satisfies that pairing there would also be a solution to the original, more complicated set of equations. And yeah. Oh yeah, last comment. Infinite number of solutions. Could we have seen that coming? Was this a surprise, a shock? No, because if you think about one of the other things we talked about last week, linear independence of vectors. Remember, the other way to look at this is this right-hand side is either in the span of these 3 column vectors here or it's not. Turns out it is. But then we ask, are these vectors linearly independent? And if you look at these first 2 columns here, 2, 3, and 6, 9 are multiples of each other. So I can make a 3, 6 vector out of a 2, 3 vector. You can kind of see that hiding in here. And that means that there's going to be multiple ways to get to this right-hand side. Linear dependence of the vectors on the left means there's multiple ways to build the vector on the right. And so we get an infinite number of solutions. I think I've seen some answers already to the chat, which is perfect. If you switch the order, would it be in? I'm guessing no. It depends on which order, because there's orders of rows and columns. You don't get to change the order of the columns because they represent specific variables. You can't mess around with those. And if we change the order of the rows to make 0, 0, 1, 1, 3, 0, 4, 2, that would not be a RREF, because the last requirement is that it be a staircase coming down. Here I have a 1, that's fine, but then the next row has to have its leading one further right. This one does not have that, it's back left. So it's that requirement here. The leading rows form a staircase from top left to bottom right. Here we're kind of going back and forth, and that's not REF. Yeah, 3 questions. So why is there allowed to be a 3? The only condition for the 1s and 0s is for the leading value in a row. So you come across this row here. The first thing you hit that's not a 0 is a 1. Perfect. The next thing here you hit, it's 0, 0, 0, and then it's a 1. So the first thing you hit from left to right is a 1. So check, check. The only other thing is that the rest of the column where that 1 is has to be zeros. There is no condition at all on the rest of the column if there's not a leading 1. This has to be a 0 because of the left to right. The first non-zero has to be a 1. But this number here could be anything else. And in fact, it can't be anything really other than a 3 with what I've got in this equation. So the leading 1 columns are highly regulated, but the other columns do not have that same restriction in them. It's just not in that description that we went through. So if you take a careful look back at each of those criteria, there's nothing about numbers to the right of the 1s. In fact, like this 4 here is fine. I got a leading 1. Anything that comes after that, barring the zeros aligned with other ones, can be anything they want to be and anything they need to be. Does the staircase matter? It helps to organize your thoughts more than anything else. No, it's not critical for the actual solution, because this has the same solution as this one here. You're absolutely right. But to organize your thoughts and to organize the yeah, basically to organize your thoughts. If you maintain the staircase, then it's a unique answer, is what the other benefit of having the staircase. If you put the staircase, there's only one possible answer. If you allow yourself to permute things, well, here I've got 2 options, and then I could go, if on a 3x3 matrix, I might have 6 options with different orders. You don't want that kind of freedom here because it doesn't add any value. It just adds complexity. Whereas if you require the staircase, there's only one answer. Your answer is going to be the same as anybody else's. And it just makes the interpretation at the end more straightforward as well. So you're correct. It's possible, but we choose not to make it that way. All right, quick follow-up, quicker question here. Here is another system. And first thing is just to remind yourself, because this is new, translating between what's on that page in matrix form and the traditional form. What kind of system of equations is this? How many equations are there and how many unknowns? Okay. Excellent, not too bad. All right. So I'm just enlarging my chat window so I can see more here. Perfect. So absolutely right. This is a, there we go. It is a 3 unknowns. In fact, it's kind of a little hint there, even the top there. The first column represents the coefficients of x1, second for x2, and the third for x3. And there are 3 rows, and each row represents 1 equation if we went back and wrote it out longhand. And so this is 3 equations, rows, and 3 unknowns, so 3 variables. And that's columns to the left of the vertical bar line. All righty. Now here we have more choices, right? We have more choices because we've got more rows to play with, but keep the goal in mind. And again, that goal is each row, there should be a leading 1. And then as we get those leading ones, we want to get rid of the zeros and the rest of that column. So to me, I latch on to any leading one I can grab right off the bat. This row 3 here is in perfect form. I'm just getting ahead of myself here. Row 1, row 2, row 3. Jeez. Row 3. This row 3 is actually lovely for a leading 1. It has a 1 first. So if we put it in the first row of our matrix, just copying it down, then we get a really nice structure. We've got our first RREF thing here. Now, after that, it's really up to you how you want to do things. I think the easiest one that I'm looking at, the easiest pairing of rows that'll give me a 0. So remember that the next goal is to have zeros in the next 2 rows in the first column. So I'm looking at this 5, 1, I'm looking at this 2, 5, I'm looking at this 2, 1, and I'm thinking, yeah, why don't I take row 1 minus 2 row 3s? Why am I doing that? Because then I get 2 minus 2, I get a 0 in that first column, and the rest of the stuff will work itself out, but I'm looking for this 1 and then 0 and 0. That's my nice RREF form. So if we do that, we get 2 minus 2 is 0. We get row 1 minus 2 row 3s. So this minus 2 of these is going to be plus 2. So we're going to get positive 1. This minus 2 of these is 3. And then this minus 22, no, plus 22 is going to be 7. It's always a good idea to check your answers at the end, but I think that's what we've got. This minus 2 of these. All right. Last but not least, it's always a good idea to wait till the end to put your brackets in as you're doing these systems of equations, because these kind of take up more room than you anticipated. Next up, we have a choice. We could do, row 2 minus 5 row 3s. Sure, why don't we do that? So row 2 minus 5 row 3s. And again, what is our goal here? I have a 1 already in this column. I want a 0 and then a 0 to go with it for the rest of that column. If I do this minus 5 of these, I'll get a 0. All right, 5 minus 5 is 0. Minus 4 minus 5, minus 4 plus 5 is plus 1. This minus 5 of these, 13 minus 10, 13 minus 10 is 3. Oh, that's interesting. Now this one I will expand out. So minus 48 minus 5 times minus 11. That's minus 48 plus 55. Oh, that is 7. There. All right. Well, that's interesting because you can already see the issue here. These two rows are multiples of each other. So what I would do there, sorry, I recopy row 1 for a second. 1 minus 1, 2 minus 11. I could do something else, but I'm going to focus on the problem, not the problem, the opportunity that we have with this particular set here. So 0, 1, 3, 7 is fine in row 2. Row 3 is not satisfactory in the RREF sense, doesn't meet all the requirements for the RREF because I've got this 1 here. So I've got a leading 1 and zeros. Leading 1, I need a 0 up top. I'll get with that in a second, but I definitely need a 0 down here. So everything else in this column has to be zeros. And so I'd have to take this row minus that row. So row 2 minus row 3. And then I will get 0, 0, 0, 0. And notice that that's okay for our RREF. We're allowed to have all 0 rows. That's what happened when we solved our equations. So yeah, let's just pause there for a sec and I will ask the follow-up clicker question. Is this our RREF at this point here? Excellent. So it's close. We have a leading 1 and zeros. We have a leading 1, but remember the zeros also have to be in the upper part, anywhere in that column. If I have a leading 1, I have to have zeros everywhere else in that whole entire column. And so I don't quite have that yet. Not RREF yet. But it's easy to get. The nice thing about the RREF is that because you have a 1 already in this column and zeros kind of to the left, if you combine this row with the row above it, you can't really break the work you've already done. Your work always gets simpler and simpler as the transformations go on. So here, row 2 is fine, row 3 is fine. So I'm actually going to keep row 2 and keep row 3. 0, 1, 3, 7, 0, 0, 0, 0. And then we have, I want to get a 0 in the spot here. So I just take row 1 and I add it to row 2. I'll get 1 plus minus 1 or minus 1 plus 1, and that'll work perfectly. So row 1 plus row 2 is going to give me 1 plus 0, 1, minus 1 plus 1, 0, 2 plus 3 is 5, minus 11 plus 7 is negative 4. Perfect. This is an RREF form. I guess the form's redundant because that's what the F stands for. So this is RREF. I've got my leading 1s and then zeros, leading 1 and then zeros, and all zeros is fine too. It doesn't have any leading 1s to worry about columns with. And so we can immediately write down our solution to this, which is x1 plus 5x3s equals minus 4, and x2 plus 3x3s equals 7. All right. Again, we have an infinite number of solutions. Solutions. And I'll start introducing the terminology that we frequently use here. If you look at the leading 1s here, what you can think of that is x1 is equal to some stuff and x2 is equal to some stuff. Notice there's no condition on x3, like nothing's, x3 is kind of hanging out here. There's no, yeah, it's in equations, but we could theoretically pick it any way we like. And so what we usually do is we call x3 is a free variable. That's a new term, free variable. And x1 and x2 are called dependent variables. And I'm just going to explore that for a second. I see the chat and I will answer that question as well. Continue here. So it's not sliding the way it's supposed to. Hold on. There we go. So why do I say x3 is a free variable? We're going to get more specific about that for the matrix form, but for now the intuition is I can write x1 equals some stuff, x2 equals some stuff. And so as soon as I set x3, so I can pick x3 any way I like, equal to 1, for example. And then immediately I get x1 has a number. What is x1? I can get it from this equation here. x1 is equal to -4 minus 5 x3s, which is -4 minus 5, which is -9. And x2 equals 7 minus 3 x3s. That's 7 minus 3, that is 4. The key thing being once we pick x3, the free variable, x1 and x2, the dependent variables were fixed. Had no choice, or were fixed. And you can get fussy about how you define these things. We will get a little fussier about how you define that, but here's the practical choice. x3 is kind of the variable that had no immediate restrictions on it, but once I do define it, I get x1 and I get x2. So, all right, let's check in on the chats here. All right. Don't you lose information? Only if there's information to be had. So if you did the same thing twice, so for example, if you had taken row 1 minus row, row 1 minus 2 row 3s, and you did it again, well, then yeah, you're deliberately canceling out terms. But here you'll notice we use 2 different rows. We use row 1 and row 3, and we use row 2 and row 3. And so those, and it didn't give us zeros until we combined these 2 rows here. So what happened in this particular case is by solving the equations, sometimes your equations cancel out. Like there's nothing you can do about it. In fact, this case here, whichever way you try to solve it, you're going to get a 0, 0, 0, 0 row when you're done. You can experiment and try it. This comes from the nature of the numbers in the original setup. In fact, what it turns out to be is that these 3 columns are linearly dependent. And so if these 3 columns are linearly dependent, there's going to be an infinite number of solutions. And the way that's going to happen is you're going to have a row of all zeros to get rid of one of the equations, one of the constraints. So it will happen by itself, basically. RREF doesn't necessarily mean it's solvable. In fact, we're going to cover a case where there is no answer to this. The solution does not exist. The right-hand side is not in the span of the others, but it gives you a form where you can instantly look at the form and go, I know whether there is an answer, and if there is an answer, I know how to extract it very easily. So the RREF is a very informative way to write out the matrix of equations. That's way more informative than the original matrix form. That's the intent. The RREF down here, you can look at it and tell a lot about the solution, how many dependent variables there are, how many independent, what the solution values are with a little work. Whereas up here, who knows, right? You look at that system of equations and there's nothing that tells you anything informative at a glance. So the RREF is just very information dense in a way that the original forms aren't. And yeah, we'll talk about the infinite number of solutions. We've got a whole breakdown approach that we'll do, I think, we'll do it tomorrow after this last example. So to set the stage, if you want to read ahead, tomorrow, my next class, Thursday? No, tomorrow. I'm losing track of time. All right. Tomorrow we'll be looking at RREF forms and how to interpret them in a systematic way. For now, we're just laying the groundwork and getting some practice at manipulating the matrices and rows. So I'll skip the clicker question for this one. It was the number of equations and number of variables. Here we're actually given a hint. that there are 4 variables and there are 3 equations for the one for each row. And we're just going to see, actually, yeah, how many solutions would this have? I'm pretty sure there's going to be an infinite number of them because there's 4 column vectors here adding up to this last one. And if I have 4 column vectors in 3 dimensions, they're going to be linearly dependent. And so there's going to be an infinite number of solutions. So we could predict that up front. All right. So we're seeing a lot of infinite number of solutions here. We'll see other ones that have unique solutions tomorrow. But for now, let's just look for our goals. Again, we're going to be building a new matrix, and that new matrix is going to need a leading one. So I look in my columns here and, oh, hey, there's a lovely leading one right here in row 2. So we're just going to grab row 2 as is, copy it down. And that's going to give us the first element that we need. Top left corner, a leading one. Now after that, oh, no one likes 7s, but I don't see any choice around it. So let's avoid the 7s as long as we can. And what we'll do is we'll take 3 row 2s minus a row 3. So again, we're looking for a 0 now. I have a 1, now I need zeros for the rest of that column, 0 and 0. And 3 of these minus that will give me 0. So 3 of that minus that is minus 1. So 0 minus 1. 3 of that minus that. 30 minus 33 is minus 3. 3 of that minus that is 0. 3 of that minus 6 plus that is 2. Correct me if I'm wrong in any of these calculations, but that looks good. Now, yeah, it's going to get ugly no matter what we do. I think I would rather do row 1 minus 7 row 2s, because then I only have to multiply one thing by 7, as opposed to this one where I'd have to multiply by 3 and the numbers get big. So row 1 minus 7 row 2s is going to give me 0 for that first leading value. This minus 7 of those, oh, that's 0. This minus 7 of that, that's 0. This minus 7 of that, that's not 0. Okay, phew. That's a plus 1, I think. And this minus 7 of these, that's plus 14, it's plus 3. Yeah. All right. Look at the leading ones. That's all fine. Oh, it's actually not quite a leading one. We're almost there with this, but not quite. So again, you may want to tidy as you go along, or you can just keep going through full bore trying to get leading ones and then zeros all in multiple operations. I'm just going to do a tidying around though here, where we say, I'm going to keep row 1 from the last one. 1, 2, minus 1. Oops, sorry, that's 10. 1, 2, 10, minus 1, minus 2. And then I'm going to multiply this by minus 1 to make everything, or the leading one positive. That's all that really matters. And I just have to be careful. It was a positive 2. Now it's a negative 2 on the right-hand side. And the bottom row is fine as is. So now we've got our leading ones. Those are all great. But where I don't have things the way I need it is, I'm put in a different color. This 2 isn't right, and this negative 1 here isn't right because they are in the same column as the leading one, and I need to get just zeros in that same column. So it's not quite RREF yet, but I can get there. Sorry, that's row 3. By taking row 1 and subtracting 2 row 2s. Taking row 1 minus 2 row 2s. So that'll, again, by doing this kind of operation, keeping the staircase, this 1 is always going to stick around. If I take it minus any of the other rows, I get to keep that leading 1. It's never going to get broken. So again, advantage of the staircase, besides other advantages, but just pragmatic here. 2 minus 2 is 0. 10 minus 2 of these, 10 minus 6 is 4, and minus 1. And then here, this minus 2 of these is plus 2. Row 2 is actually fine, so we'll keep it as is, 0, 1, 3, 0, 2. And row 3, oh, row 3 was fine, 0, 0. Oh, right, we're almost done. I still have to take one more step to get rid of this negative 1 here. So that'll be row 1 plus row 3 now. a bit of space. There we go. And if I do that, we're almost there. So here, look at this diagram over here now. 1, 0. 0 plus 0 is 0. 4 plus 0 is 0. Minus 1 plus 1 is 0. 2 plus 3 is 5. Row 2 is already fine. 0, 1, 3, 0, 2. Row 3 was already fine. 0, 3. Row 3 was already fine. This is now an RREF. Oops. So R2 equal minus 2. Oh, thank you. R2 does minus 2. Thank you for that. Yes. This row here, it was -2 on the right-hand side. So very easy to slip a value out there.
Where did the 4 in the first row go?
I lost it. I forgot it. Thank you.
Oh, sorry.
Nope, no, don't apologize. You found the mistake. So that's great. Yep, absolutely. That 4 is just a copy across because you take all of row 1 minus row 3, but that's 4 minus 0. Absolutely stays a 4. Excellent, excellent catches. Sorry, I'm looking at the time going, I got to get it done in 2 minutes. Not unlike maybe people writing tests, but all right. And so I won't keep you longer than this little bit here. Again, we can read this off. Now we have 4 variables. So I'll just put it under here, x1, x2, x3, and x4. And out of this, we get from the first row, we have x1 plus 4 x3s equals 5. That's leading 1, leading 1, leading 1. And we have x2 plus 3 x3s equals -2. And last but not least, we have x4 equals 3. So that one's nice and fixed. It's dependent. And again, you can kind of see once I know x3 in this case, what's special about x3, it does not have a leading 1. But once I know what x3 is, I can always put it the other side and I'll get x1 and x2. So I don't want to hold you late here, but I'll just add some notes here afterwards. But basically, we're going to ask you to do this procedure on matrices to help solve systems linear equations. And tomorrow, we're going to go into the analysis side of this. So being able to look at the row reduced echelon form, the RREF, and saying, oh, I know what this means for those 3 cases we looked at. No solutions, single solution, exactly one solution, and infinite number of solutions. All right, we'll stop there and I will open the floor for questions after I go back to that slide in case people are still copying. There we go.